So, welcome to the next lecture in mechanical operations. This will probably be the last lecture in our discussion of mechanical separations. We have so far discussed screens and sieving and then filtration. So, today we are going to talk about the third method of mechanical separation, which relies on the motion of particles through a fluid. So, we are going to talk about settling or sedimentation, which is a method of separating particles based on the velocity with which they travel in a fluid. In one of the earlier lectures, we talked about the terminal velocity, which particles reach, but not immediately. That is a steady state velocity, right, because there are basically three forces acting. There is a gravitational force that pulling the particle down, and then there is a drag force and the buoyancy force, which are opposing the settling motion. So, at time 0, you are not going to be at steady state. There is going to be a rate of change of velocity of the particle with respect to time, which has to be balanced by these other forces. So, you can write it as some mp dvp by dt equals the gravitational force, which is pulling it down, minus the drag force minus buoyancy force. So, there is an initial transient. When you set the particle in motion, it is going to either accelerate or decelerate until it reaches a certain velocity, and after that you are going to be at steady state. Now, the initial transient can be quite long or it can be quite short, depending on the character of the particles and the character of the fluid and so on. But a settling apparatus depends upon the relative motion of particles and the differences in the velocities associated primarily with size and density, although shape can also be an important parameter, but for the purposes of this discussion we are going to assume that all particles are spherical. So, in a gravitational settling apparatus, what you are relying upon is the motion of particles through a stationary fluid or a fluid that is moving with a very low velocity. And so, there is a lot of time. The residence time of particles in the settling chamber is quite long, and so it gives ample time for the separation to happen. However, the drawbacks, if you are just using gravity settling, is that the process can be quite incomplete, the separation process in particular, because the effect of gravity on two particles that are only slightly differing in size or density characteristics may not be that significant. So, you can get quite a bit of overlap. And the other problem is you will start collecting a sludge at the bottom of the chamber, and that can be very, very difficult to remove. And so, if you are interested in the sludge as well, in addition to the clear filtrate, then you really need a process that will continuously remove the sludge as it builds up, so that you can put it to some productive use. And so, gravitational settlers are currently mostly being replaced by centrifugal settlers. Centrifugal settling chambers kind of address both issues. They provide an additional effective gravity which can pull down the particles much faster, and the fact that you have centrifugation happening means that the particles that are settling are never going to be stationary. They are not going to have time to get bonded and solidified. They are going to be in a state of flux. So, it is very easy to change the setting so that the material that is collecting at the bottom is sloughed off and collected elsewhere. Now, coming back to gravitational settling, settlers can essentially be used for two purposes, and depending on the purpose they are classified as clarifying settlers or classifying settlers. In a clarifying settler, the purpose is to remove all particles from a fluid, whereas in a classifying settler what you are trying to do is separate particles by size. A classifying settler is frequently required for analytical purposes. If you are trying to estimate the size distribution of a sample, then clearly you need to be able to classify. On the other hand, if your objective is simply to purify the fluid and remove all particles from it, then a clarifying settler works just as well. And in fact, a clarifying settler, basically what it does is it takes a suspension of particles in a fluid and it subjects them to a separation process which demarcates two layers. So, you concentrate particles in the bottom layer into a sludge, so that the top layer is now a clear liquid. And so, these types of clarifying settlers or sedimentation equipment can be called thickeners or they can be called clarifiers, depending on whether your primary interest is in the separated solids or in the purified liquid. If depending on what is the most valuable output from your process, you tend to focus on one or the other. So, when you talk about these types of classifiers, again they can be classified in two ways. One is a gravitational classifier and the other is a sorting classifier. In a gravitational classifier, you tend to separate particles based primarily on size. So, size is the classification parameter, whereas in a sorting classifier you classify or separate primarily based on density. Okay. Now, if you think about when you would want to do what, suppose you have a particle mixture and you are trying to separate, when would you, or what are the typical applications where you would separate by size versus what are some typical applications where you would separate by density? I mean, clearly there has to be a fairly steep density gradient in your mixture in order for density based separation to be effective, and similarly there has to be a fairly wide particle size distribution for a size based classification mechanism to be effective. Particularly when you talk about density based classification, that can again be subdivided into two types. One is called the float and sink method and the other is called a differential settling method. In a float and sink method, I mean, as the name suggests, what you try to do is select a fluid and suspend the particles in it such that the density of the fluid is between the density of one of the materials and the other material. So, clearly the heavier material would sink, the lighter material would float, right. So, you get separation between the two. Sounds like a very simple process and should work in principle, right. So, what do you think could be the difficulties in this kind of float and sink classification? Anything that you can think of? What would be the challenges, let us say? The challenge is finding a fluid that has a density that is between that of two solid particles, right. Fluids, I mean even liquids typically have densities that are much smaller, lower than that of solids. So, I mean there are some liquids that naturally have a high density. There are some high molecular weight hydrocarbons, halogenated hydrocarbons that have a high density. Calcium chloride can be made to be a high density liquid as well. But more commonly what people use in a float and sink apparatus are synthetic liquids. So, what you do is you take a liquid like water and actually prepare a suspension of particles in it to give it a uniform density that is between the densities of the two materials that you are trying to separate. Now, what do you think will be the difficulties with that? Well, whatever solid you are adding to increase the density becomes a kind of an impurity in the process, right. So, now it becomes a three-way separation process. You have to separate material A and material B, which is what you are trying to separate based on density, but now you have this material C as well, which is the particles you have added to prepare the suspension. So, you have to have an effective separation or removal process for this third material as well. So, that takes some ingenuity to prepare. but it is a good process to use, as I said, when the density gradients are very steep. So, an example is coal cleaning. Coal is actually a very lightweight material, it tends to float on water. However, many of the impurities in coal are very heavy. For example, ash, which is the mineral constituent of the coal, which can survive the combustion process. So, if you are trying to separate coal from ash or from some of the other mineral and metallic impurities that may be in the coal, a float and sink method works very well. So, typically the way you would do that is take the coal as mined, wash it to separate, to loosen impurities from the coal including ash, and then use a float and sink type of apparatus to separate the coal as the floating material from the impurities that will then sink to the bottom. Ore beneficiation in general uses the float and sink method quite extensively. The other method, which just relies upon differential settling, just makes use of the fact that if you have multiple materials of roughly the same size, then their settling velocities, terminal velocities will vary depending on the density, and therefore you should be able to effect a separation based on their differential settling rates. So, you could collect particles as a function of time. You could collect particles during a time interval that is tuned for the fastest settling particle, remove all of them, and then collect the slowest settling particles and remove all of them, right. Now, what would be the challenge in that? It works perfectly when particle sizes are identical, but as you know, that type of a monodispersed particle population is almost impossible to achieve. So, in addition to there being a density gradient, there is likely to be a size gradient as well. So, you can imagine that if you look at the settling velocity of a particle, size and density play a role. So, a lighter particle with a larger size will settle at the same rate as a heavier particle of a smaller size. So, that is the error in this method. In fact, if you remember the equation for settling velocity or the terminal velocity of a particle, it goes as dp squared times rho p minus rho f times cc over 18 mu times g, right. So, if you have two particles in your system, let us say that this is P1, dP1, rho P1. Of course, the Stokes-Cunningham correction factor also will vary for the particle, and similarly you have a Vt particle 2 equals dP2 squared times rho P2 minus rho f times Cc2 over 18 mu g. And suppose you want to look at particles that will settle at the same velocity. In other words, equate VTP1 to VTP2, then what do you get? Basically, you will get that dP1 squared over dP2 squared equals rho P2 minus rho f divided by rho P1 minus rho f times Cc2 over Cc1. And let's take the case where rho f is very small compared to rho p. Both particles, and by the way, this type of differential settling classifier, the fluid density is always kept lower than that of either of the two particles that you are trying to separate. How about, as we have seen before, the Stokes-Cunningham correction factor, particularly for small particles, is proportional. How is it related to particle size? 1 over dP, right. So, this you can write as dP1 over dP2. So, if you take that to this side, basically what you get is under equi-settling conditions, dP1 by dP2 equals rho P2 by rho P1. So, what does that mean? If you plot dP versus the terminal settling velocity. Let us say that one particle has a trend like this and the second particle has a trend like this. The same Vt can then be achieved for two different particle sizes depending on the rho p value, right, because each of these corresponds to different densities. This is rho p1 and rho p2. So that is a confounding factor in this experiment. So how do you then apply this methodology? I mean, clearly the particles with which you are going to have trouble are those that satisfy this condition approximately. So you have to sort of analyze the particles that you have in your system. You have to collect the samples, do a particle size distribution analysis, you should do a density analysis and identify the possibility of this happening in your mixture. It may be that for the system that you have, this will never happen, in which case it is fine, you do not have to worry about it. But if the densities and the sizes are such that this condition will be satisfied, you have to be aware that particles that are settling at the same velocity may have entirely different densities based upon their sizes. Okay? So just keep that in mind. So I mentioned that when you have a differential settler, the way that you can segregate the particles is actually two ways. You can have a column and with a liquid in it, introduce a bunch of particles of either same size or different sizes, same density, different densities, and then you have a collector at the bottom and you kind of withdraw this collector at different time periods, and you can actually calculate how long particles of different sizes will take to get to the bottom pan. So you can collect up to a certain time that corresponds to a certain size that you want to separate. So all particles that are heavier than that or larger than that size or heavier than that density will collect within that time. So that can be your product A, and then anything that settles afterwards will be your product B. So you can achieve separation not just between two sharp sizes, but you can achieve separation at a size where all particles in one of your collected material is smaller than that size or lighter than the density, and in your other collection chamber you will have particles that are either larger than that size or heavier than that density. So this type of separation is possible just based on settling characteristics. But you can also think about doing something else, and that is have taps or outlets along the height of the column. This method is known as Beaker decantation. You will actually do an experiment using this technique in MO lab next semester. It also takes into account the fact that particles in your lab experiment, by the way, you will be given particles that are of the same density. It will be the same material, so presumably same density. So you will be primarily looking at the effect of size on the separation characteristics. But in this, what you would actually be doing is sampling the liquid at different heights as a function of time, and that will clearly also give you an indication of how particles are getting separated along this settling column. Again, what you will do is you will look at settling time as a function of velocity. So you will actually calculate for different times what would be the rate at which particles of different sizes would have settled, and then you will compare your results, experimental results, with theoretical predictions based on particle mobility and see if you are getting good results. What can affect the effectiveness or efficiency of a settling process? There is something called hindered settling. Hindered settling is something that will affect your results, particularly as your concentrations increase. I think we talked about this briefly in one of the earlier lectures. If the average distance of separation between particles in a suspension decreases, there is a greater chance that one particle will interfere with the settling behavior of its nearest neighbor particle, and it can either be an inhibition effect or it can be an acceleration effect as well. Now, when will acceleration happen? When the particles get close enough that they actually stick to each other. When aggregates form, when agglomerates form, you are effectively increasing the particle size, right. So, as the size increases, the settling velocity will increase. In fact, I mentioned that one of the drawbacks of a gravitational settler is that particles settle very slowly, and sometimes when you are not so interested in classification, but in clarification, you want the particles to settle fast, you do not care if they agglomerate. You in fact you want them to agglomerate so that they will settle fast. Then you use materials called flocculants. Flocculants are essentially settling aids that do the reverse of what we have talked about before. When you have cohesion and you are trying to avoid cohesion, you try to coat the particles with some material that has low surface energy so that the particles will repel each other, right. A flocculant serves the exact opposite purpose. It actually promotes cohesion between adjacent particles. So, typically these would be like ionic solutions. They will build up a charge distribution on the particles and make them attract each other. They can also be solutions that contain high molecular weight polymers. Again, the higher molecular weight of a polymer will increase its adhesion characteristics and therefore make it possible for cohesion to happen. So, there are these materials called flocculants that are very widely used in industry, again not for classification. For classification this would defeat the purpose by causing coagulation to happen, but for clarifying, where you are just trying to get as many particles off the liquid as quickly as possible, these flocculants really serve the purpose. And what they promote is hindered settling. They draw the particles very close to each other until they actually touch, and they start forming these aggregates, and then they start settling in aggregate form. Now, the bottom layer that you get when you are using a flocculant, or when there is significant hindered settling, the nature is very different from the solids that you get without hindered settling happening, in the sense that it is very porous, because when you form a particle aggregate, there is always space between the particles, right, which is filled with gas or fluid, and so the density of the agglomerate is much lower than that of the individual particles. The porosity in the aggregate can be quite high. So, what that means is the layer that forms at the bottom will have very different characteristics. It will be highly porous, it will also be very compressible. As time passes, the deposit will get more and more compressed and become more and more solid, will keep increasing in density and so on. So, it is again very important, particularly when you are using flocculants to increase hindered settling, to try and remove the layer that forms as quickly as possible, because as it solidifies, as it compresses, it will become increasingly difficult to remove from the solid surface. Okay. The way that sedimentation happens is, particularly when you are trying to do what I would call continuous sedimentation, there are batch settlers and there are continuous settlers. A batch sedimenter basically looks like this, and this is what you will use in the lab experiment. It's a vessel, it's used in batch mode. You take a suspension, pour it in, and allow separation to happen, right. But in industry, frequently you also need to use what are called continuous thickeners. In a continuous thickener, there is not only the particles are moving down, not only by sedimentation, but the entire liquid is also moving down, typically at a lower velocity than the settling velocity, but there is a net downward movement and fresh liquid is coming in all the time. When this is happening, clearly the rate at which the particles are being driven in the settling process is going to be greater than if you have a simple static settling process. The picture of how the separation happens over time, it actually happens in several stages. So, if you take a beaker and you fill it with particles that are suspended in a liquid, let us say, initially you will see a very uniform concentration of particles that are suspended in the liquid. This is at t equal to 0. Now, if you look at the same solution, let us say at T1 greater than 0, what is going to happen? There is going to be a stratification starting to happen. There may be multiple layers and a clear liquid at the top. The stratification will happen based on size and density. The heaviest materials will be in the bottom layer, the next heaviest, and so on, or conversely the largest particles will be at the bottom layer, and so there will be a distribution of densities and sizes in this layer, but a clear fluid will start to emerge. So, now if you look at it after time t2, the clear layer will be expanding and then the solids layers will be starting to compress down, and if you keep going, at t equals, let us say Tf, which is when your separation process, your classification process or your clarification process ends, what you will see is there will be one clear layer and one sludge layer. The sludge layer will contain variety of sizes, variety of densities. The clear layer will be virtually free of particles, because except the very lightest, you may still have nano sized particles in the clear layer, but most of it would have gone down. So, again, one of the experiments you will do in the laboratory is to look at how this interface moves as a function of time. So, if you call this height z, which is the distance between the bottom of your container to the bottom of your clear layer, that height keeps decreasing as the clear layer moves down. So, a parameter that is very important to measure is this dz by dt, which gives you an idea of the rate at which settling or sedimentation is happening. So, in a continuous thickener, what is the net downward flow rate of particles? There are actually two components to it. It is called GT plus GS, where GT is the downward movement or downward flux of particles due to transportation. In other words, the entire liquid is moving down, right. In a continuous fluid, this fluid it's actually moving with a velocity u in a continuous thickener, and that downward motion, because it is carrying particles along with it, induces a downward flux. But in addition to that, there is a sedimentation flux. So, the net flux G is the sum of the convective flux GT and the settling or sedimentation flux GS. So, you can write this GT as C times U, where C is the solids concentration in the liquid and U is the rate at which it is moving down, and GS you can write as C times dz by dt, where dz by dt is the rate at which the interface between the clear layer and the particulate layer is moving down. So, in other words, G is equal to C times U plus dz by dt. If you plot this, and by the way there are two parameters you should be aware of. If you plot t versus z, the rate at which the interface is moving down, what kind of trend do you think you will see? Think it will be like this, or it will be like this, 1, 2, 3. I like these voting things. How many think 1? How many think 2? 3? I think I always give the right choice as 3, that is why you guys always choose the third one. But yeah, so the correct answer is 3. Initially the layer will move down fast, but then it will slow down because of the compression effect. You are building up solids in the lowermost layers, and they provide resistance to the additional settling of particles from the layer above. So, you will see a slowing down of the settling. Supposing you plot G versus or sorry C, concentration of solids, versus let us say these 3 parameters. First GT, now clearly that is linear, right. So, GT is simply proportional to C. So, for a given U value, GT will just increase linearly as C increases. How about GS? So, I will give you choices. So, GS can also be like this, or it can be like this, or can be like this 1, 2, 3. How many think 1, 2, 3, 0? How many have no opinion? No, but think about it. Let us go back through these choices again. How many think 1? Just think about it, just intuition, right. There is no science here. You can do this experiment in your room or your kitchen. We are talking about the rate at which the interface between the clear liquid and the sludgy liquid moves down. As concentration increases, 1. How many say 1 now? 2 and 3. Okay, I think 2 had more show of hands, so we will just go with 2. But the correct answer is 2. It actually goes through a maximum and then comes down. Why is that? As you can imagine, as you keep increasing concentration, again you keep everything else constant, initially there is going to be an increase in the rate at which settling happens. But then what is going to happen? Again the sludge is going to start filling up, and when you have higher concentration, the sludge fills up to a greater extent, faster, and it also starts exerting a higher upward pressure, right. So, GT will actually go through a maximum and then start to drop. So, if you look at G, what type of behavior will that have? So, clearly it is going to track this for a while, and then it is going to go down, and then it is going to basically at some point the that is a little too confusing. So, with C, this is GT, this is GS, the settling flux, and so the total flux is going to look like this. Eventually it will just catch up to GT because GS will go to 0, right. So, the total downward flux of particles will actually have a minimum here. How do you size the equipment? That is where this parameter G min becomes important. One of the critical things is in any kind of a batch settling experiment or a continuous settling experiment, what is the area that is available for settling to happen. In order to find that area, you have to base it on the minimum flux, not on the maximum flux. And the way you do that is you take the feed rate F times C0, which is the solids concentration in the feed, and this is the feed flow rate, must be equal to A times G min, where A is the area of your sedimentation apparatus and G min is this minimum solid flux that you have obtained. So, designing your sedimenter, the parameter A will be equal to F times C0 divided by G min, okay. So, that is a design parameter that you can establish, I think basically experimentally. This GS is something that is very hard to calculate a priori. I mean you can, but it is better to obtain the data experimentally, and then of course GT is fairly easy. I mean once you know the velocity at which the continuous flow is moving, you can always estimate GT. So, calculate G, draw these curves, find the minimum in G value and size your equipment based on the minimum. Otherwise, what is going to happen? Your total area is not going to be sufficient to handle the flow rate that is going to be happening in the or the solids flux that is going to happen in your system. Okay, so there are some interesting things you can look at with this expression. You know, what does it mean when GS goes to 0? What if GT goes to 0? If you have a batch settling, then this part just drops off. In a batch settler, how will G look? It's same as GS, right? So, a batch settler works very differently. In a batch settler, there is no minimum, you just have a maximum, and so how do you size your equipment for a batch settler? Anyway, think about it. I think sedimentation, what we have talked about so far is gravitational sedimentation, right. So, we will briefly touch on gravitational sedimentation in the next class, and then we will start talking about size reduction. And in fact, there are some interesting convergences between size reduction methods and separation methods that we will also talk about in the next week. Any questions? Okay, see you in the next lecture.